We've looked at what it means for a function to be continuous, so now let's look at how functions can fail to be continuous. Effectively, there are three things that can go wrong. In the first case, our function might be well behaved but contain a hole at the point C. Such points are called removable discontinuities, in effect because if you plug the hole, you could remove the discontinuity. Mathematically, these are characterized by the fact that the two-sided limit exists but isn't equal to f at the point C. Next up are jump discontinuities, where the function makes a leap from one side of C to the other. In this case, both one-sided limits exist, but they don't agree with one another, and their difference is precisely that jump that we see. Finally, when the function is so poorly behaved that even the one-sided limits don't exist, we say that C is an essential discontinuity of F. Okay, so let's write this out mathematically. Let's suppose that f is a function which is not continuous at the point C, and define L plus to be the limit at C from the right, and L minus to be the limit at C from the left. We characterize the discontinuity of C as follows. It is removable if L plus and L minus both exist and are equal. It's a jump discontinuity if both one-sided limits exist, but they are not equal. And finally, it is an essential discontinuity if one of the one-sided limits does not exist. Now we've already seen an example of a function with a jump discontinuity in the form of x divided by the absolute value of x. The issue occurs at the point x equals 0, where if we take the limit from the right, we get plus 1, and if we take the limit from the left, we get negative 1. To remind you of the jump, let me graph the function for you here. The function is constantly plus 1 to the right of 0, and negative 1 to the left of 0, giving that jump right at 0. So we've seen examples of other discontinuities as well, but let's tackle them in a single example. Let's look at this rational function and classify its discontinuities. As it will be useful, let's factor both the numerator and denominator into their linear terms. Looking at the denominator, the points x equals negative 2 and 3 will be discontinuities. The reason for this is that we know we can't divide by 0, and the function doesn't provide alternative values for these points. Looking at x equals negative 3 first, we can compute the limit in the usual way, taking advantage of the fact that both the numerator and denominator have this x minus 3 term. So if we cancel these out, that gives us a limit of 7/5. Since the limit exists, that means x equals 3 is a removable discontinuity. In the case when x equals negative 2, there's no term in the numerator which can cancel out this singularity. This in turn will imply that the limits from both the left and the right will fail to exist, hence making x equals negative 2 an essential discontinuity. To show you this again, let me graph the function of f for you here. We've got this hole at 3, and our function shoots off to plus or minus infinity at negative 2. And these are the bad points, as we expected. So by analyzing the one-sided limits, we can determine how a function fails to be continuous.